Well, in this FE review, we'll look at indoor air quality. Now again, the section of the FE reference handbook will somewhat vary, but for this section, most of it really is within the environmental engineering section. So, a number of the problems that you may very well encounter are based on your knowledge. The answers are not in the reference handbook, so you're going to have to rely on previous course material, what reviews you've done, or just thinking through the problem and using common sense. So in this case, we have a building that has been recently constructed and opened. Of the compounds listed below, you're asked which is not likely to be an indoor air pollutant. So, information that's important is that the building was recently constructed and opened. And the choices are formaldehyde, xylenes, toluene, and lead. The correct answer is lead. And formaldehyde, xylenes, toluene, formaldehyde can all be produced from flooring materials, carpeting materials, paints, upholstery. Can be released, especially when these are new materials, and it's not unusual to find concentrations in new buildings. In fact, it's referred to as new building syndrome of these chemicals. Lead, we don't use leaded paint anymore. We don't use leaded gasoline. So it's very unlikely that you would find lead in this environment. So in this question here, again, it's one of these general recall type questions. And you're told that formaldehyde is a common indoor air pollutant. And you're asked of the following sources which is not likely to be a significant source of formaldehyde. And the choices that you're given are medium density fiberboard, particle board, photocopy machines, and fiberglass machines. The answer is photocopy machines. Photocopy machines release ozone. The others all release formaldehyde. So in this question here, again, another recall type question, you're told carbon monoxide is a common indoor air pollutant. Of the following sources, which is not likely to be a significant source of carbon monoxide. Important thing to remember here is that carbon monoxide is released by incomplete combustion, so it's a product of combustion. So if you look, gas ranges, ovens involve combustion, wood burning fireplaces involve combustion, as do kerosene space heaters. So the answer is particle board. And the last of these types of questions, we have numerous pollutants are emitted due to cigarette smoke, and of the following pollutants which is not likely to result from cigarette smoking. We just talked about that carbon monoxide is released from combustion processes. Cigarette smoking is a combustion process, so carbon monoxide is released, as is particulate matter and also formaldehyde. The correct answer is arsenic. So the next set of problems we'll look at pertain to mass balance, or pertain to really to computational type problems. Really mostly they do stem from a mass balance approach. The first equation that we'll look at is from the environmental engineering section. In fact, all of the equations that we'll look at in this unit are from the FE reference handbook environmental engineering section. So we have looked at mass balance throughout a number of your courses. You've started in E&E 280, you've looked at those in E&E 489, 483. Approach is identical. Couple things to remember here. Okay, this is written as V dc dt. Remember, We've taken volume out of the differential, so we've assumed that we have constant volume. That first term, Q C naught, that is the term for the input of your contaminant of interest from the outside. So we have a flow in, and in this case, C naught is the concentration of the pollutant in the outside air. We have a source term inside, and we have a term for the pollutant leaving. So Q in equals Q out, so we'll just use Q. And this problem uses C sub I for the indoor concentration of the pollutant. So let's note the nomenclature is a little different from what we've used in courses. And then the last term describes first order decay. So we've used KCV, so K is the first order decay constant, C sub I, the concentration in the system, and V is the volume. We've also noted in here, we've assumed that the concentration leaving is equal to the concentration at any point in the system. So we've also assumed that we have a completely mixed system. Now the equations that they're giving you here are a little bit different in formulation. They use a term, tau, the time constant, and note that that is just A plus K, and A is the air changes per hour, so the air exchange rate, K is your decay constant. Make sure your units are consistent. And then the steady state concentration, note, is written in terms of tau, the air exchange rate, your concentration entering the system, plus the source term divided by volume. It's identical to what we've done in our classes. It's just a slightly different formulation. Same thing here, slightly different formulation from what we have done in class. The one thing to note with this is that it's assuming, this formulation here assumes that the concentration at time 0 is equal to the outside concentration. So that's an important caveat in this formulation here. And then it also provides you with some information about the air exchange rates into homes. So it gives you various different conditions of the room and how that might affect the air exchange rate. So let's do a first problem here. We have a situation where we have an unvented kerosene heater and it's operated for 4 hours in a cabin, and you're told that the volume of the cabin is 200 cubic meters. The heater emits SO2 at a rate of 50 micrograms per second. The outdoor air concentration is 20 micrograms per cubic meter, and the concentration in the cabin when the heater is lit is also 20 micrograms. So that's what I just mentioned, that we're assuming that initial concentration is the same as the outdoor air concentration. You're told that the air exchange rate is 1 air change per hour. You could, in one of these problems, be told something about the configuration in the room, in which case you'd have to look up the air exchange rate. And you're given a decay rate for SO2, and you are asked for the indoor air concentration at the end of 4 hours. And we're going to assume, as we just discussed, that the cabin is well. So let's look at this problem. We'll write down the parameters. We have volume is equal to 200 cubic meters. Their source term is 50 micrograms per second. We want that in mass per hours. So if we multiply that by 60 seconds per minute and 60 minutes per hour, then that is equal to 18,000 micrograms per C0, concentration in the outdoor air, you're told is 20 micrograms per cubic meter, and we've said that that is the concentration when the heater is lit. You're told that the air exchange rate is 1 air change per hour. You're given a decay constant in inverse seconds. Again, we want that in inverse hours, so we'll multiply by 3,600 seconds per hour, and that is equal to 0.23 inverse hours. The first calculation we need to do is to determine tau, and that is equal to A plus K minus 1. So that is equal to 1.0 plus 0.23. Taken inverse of that sum, and that is equal to 0.813 hours. And we'll calculate the indoor concentration at steady state, and this is because of the way that the equations are given here. And that is equal to tau A C0 plus S over V. You could derive this based on what we've done in class, but since you've given this equation, we'll use that, and that is equal to 0.813 hours times A 1.0 inverse hour times C0, which is 20 micrograms per cubic meter, plus S, which is 18,000 micrograms per cubic meter, divided by the volume, which is 200 cubic meters. And we need to close those parentheses. And that is equal to 747 micrograms per cubic meter. And then you give an equation for CT, so the concentration at time t, and that is equal to CISS 1 minus e to the minus t over tau plus C0 e to the minus t over tau, and that is equal to 747 micrograms per cubic meter times 1 minus e to the minus 4 over tau, which is 0.813, plus C sub 0, that's the 20 micrograms per cubic meter, times e to the minus 4 over 0.813, and that is equal to 743 micrograms per cubic meter. So that is the correct answer for this problem. So in this next problem here, which is actually taken from the industrial hygiene literature, it's an attempt to determine the relationship between the number of people working in an office complex, the concentration in this indoor space after a long period of time of human occupation. So for instance, it could be just people are leaving for lunch. It could be at the end of the day. And the concentration in the outdoor air. And what we can determine from this is an approximate flow rate of outdoor air. So let's look at this next problem. And in this case here, you're told that the minimum classroom size for 20 students and 1 teacher is 900 square feet with a 9-foot ceiling. The ambient CO2 level is 420 parts per million. The maximum desired CO2 concentration in the classroom is 800 parts per million. I could even say that it should be lower than that, but at 800 you start to see children get sleepy, lack of focus, so we want to make sure that we keep that concentration less than 800. And given that, the required air exchange rate is most nearly, and you're given a number of choices. So let's look at this problem here. So again, using their notation, C sub OA, or the concentration of CO2, and we're using CO2 as a tracer gas, is 420 parts per million. C indoors, so that maximum concentration that we desire is 800 parts per million. N is equal to 21. We have 20 students plus 1 teacher. And then it's just, we can calculate QOA is equal to 13,000 times N, so it's 21 students that we have, divided by 800 minus 420, and that is equal to 718 cubic feet per minute. And just note the units here. So the way that this is written is your answer, your volumetric flow rate is in cubic feet per minute. You were asked for air changes per hour. So A is equal to 718 feet cubed per minute. There are 60 minutes in an hour. And we will divide this by the area. So we have 900 feet squared times a height of 9 feet. And that is 5.32 air changes per hour. So that is the correct answer here. This next equation actually comes from ASHRAE, and ASHRAE is the American Society of Heating, Refrigerating, and Air Conditioning Engineers, Incorporated, and they have a standard, and it's ASHRAE 62, which pertains to ventilation levels for acceptable indoor air quality. And this provides recommendations for the minimum amount of air that is needed per person in defined spaces. So one way that we can calculate the amount of air that we need is with this equation here. So again, CO2 is used as a tracer gas. It's easy to measure. And we can measure the CO2 concentration in the return air, in the supply air, and the CO2 concentration in the outdoor air. So we're looking at using outdoor air in order to bring in fresh air to provide a cleaner, refreshed atmosphere, also used to prevent or to reduce potential exposure to any sort of infectious disease. So we have a problem here where you are told that the environmental engineer takes 3 samples with the following air values. So the outdoor air CO2 level is 420 parts per million. The supply air has a CO2 level of 645 parts per million, and the return air is 850. And you're given a number of choices again, and then the question is, what percent outdoor air do we need to provide? And the percent outdoor air is just the concentration of the CO2 in the return air minus the concentration in the supply air divided by the concentration in the return air minus the concentration in the outdoor air, and we'll multiply that by 100 to get percent, and that is 47.7%. So that is the correct answer there. The final problem that we'll look at again is from a ASHRAE industrial hygiene type problem. Again, you're given this equation here, and here we can determine the number of air changes that are required to maintain a certain level of pollutant. In this case, we'll look at CO2, so it's based on CO2 levels, again as a tracer case, and it's also based on an exponential decrease in CO2 levels over time. And what we measure is we measure the CO2 at the start of the test, we measure the outdoor concentration of CO2, and we measure the concentration of CO2 at the end of the test and the time lapse between the start and end of the test. So we have, again, a set of data that's provided to us. So we have an environmental engineer conducts a test to determine the outdoor air changes per hour. So we have a CO2 level at the start of the test. We have the outdoor CO2 concentration. We have the concentration at the end of the test, which is 2 hours. And you're asked for the number of outdoor air changes per hour. Again, you're given a number of choices. So again, let's just write this, and we'll use their notation. So C sub I is the concentration of CO2 at the start of the test. C0 is the concentration of CO2 from the outdoor air, so it's concentration outside. C sub A is the concentration at the end of the test. And the length of time is 2 hours. So solve this. N is equal to ln of 2,200 minus C naught, which is 420, minus ln of 430, so the concentration at the end of the test, minus, that's 420, there shouldn't be a decimal there, and we'll divide that by 2.0 hours, and the answer is 2.59 hours, or with the choices you had, it was 2.6 hours. So these are type of problems you might see in the indoor air section of the environmental engineering FE. So good luck. If you have any questions, I will post this again on YouTube, and feel free to send me an email or even ask questions in the comments. Thank you, and have a great day.